So thank you, Cleto, for the nice invitation. It is a pleasure to be virtually in Brazil. I also very happy to be able to talk about these questions and problems on symbolic powers. It's an area that I found very interesting for research. And this project in particular is that I'm going to talk about is a joint project with Cleto and Uwe Nagel at the University of Kentucky. And Cleto, honestly, has been a driving force for this project. He was the one who essentially started the project and who really essentially made this project happen. So I'm very, very happy to be able to talk about it today with you. So for simplicity, for the purpose of this talk, R will always denote a polynomial ring over the complex numbers. I will be a radical ideal. All the associated primes will have the same codimension, the same height. And the actual assumption in which one could prove the statements are that R is actually a Comic-Macaulay ring, either standard graded over a perfect field or local, and unmixed, and generically a complete intersection. You don't need to know what all these words mean, just want to give you an idea that the statements work in higher generality. Then I will discuss. So the talk will have 4, possibly 5 parts, depending on my time management. The first part is what are symbolic powers? So we get a feeling of what they are. Why do we want to study symbolic powers? Third part will be a formula to try to help computing symbolic powers. The fourth part will be effectivity of the formula. And then if time permits, we will discuss a nice conjecture. So first of all, what are symbolic powers? So once you given an ideal I, as we said earlier, for instance, a radical ideal, there are 2 different types of powers we can produce. We can create the ordinary power, which is just the ideal generated by the product of m generators of I, or the symbolic power, which, remember, I is the intersection of primes, while the symbolic power will be just taking the first prime to the m power, intersect the second prime to the m power, and so on. Okay. And 2 really basic remarks are that the first ordinary and symbolic powers are both equal to I, and in general, the ordinary power is contained into the respective symbolic power. In general, though, they don't need to be equal. For instance, let me give you this example. If I is the ideal defining 3 coordinate points in P2, if you're familiar with this, or otherwise you can just look at this as a nice square-free monomial ideal. Consider this ideal in a polynomial ring, let's say in 3 variables, then I squared, well, it's generated by, for instance, the square of each generator and this product of any 2 different generators. So you can write all 6 generators easily. And if you try to compute the symbolic square, the second symbolic power, well, by definition, you need to take the first ideal and square it, second ideal and square it, third ideal and square it, and then you need to intersect them. So we have a nice kind of primary decomposition way of defining the ideal, but it's not super clear what the equations will be. And in this case, it turns out that what we need is to take I squared, and then we need to add 1 more generator, 1 more monomial, xyz. If you check, xyz is indeed the product of, it's inside each of these ideals. It's the product of any 2 of the generators. It's a multiple of them. So this is an example where the symbolic square is strictly larger than the ordinary square. And in this case, the symbolic square, maybe I shouldn't do this, is actually equal to I symbolic squared intersection an extra component. So in terms of primary decomposition, we got extra stuff, so to say. Okay. So here is an example. And another example is actually, let's say, if I take the ideal xy comma zw in a polynomial ring with at least 4 variables, then in this case, it's not hard to see that the symbolic square and the ordinary square are the same. So this is to say that in the remark, we have a natural inclusion between IM and I plus symbolic M. And sometimes it is an equality, sometimes it is not. So the fact that I want to mention here is that if I is a complete intersection, meaning that the height of I equals the number of generators, then it is always true that the M symbolic power and ordinary power are equal. So one example is this idea, okay? The previous example is one of these complete intersections. The height is 2 and the number of generators is 2. So that explains why the ordinary and symbolic squares are equal in this case. Okay. So this is just a very basic minimum definition to understand what are symbolic powers. Now, the question is, why do we care about symbolic powers? And the short answer is that they encode relevant information, which is, of course, a fantastic generic answer to give, but it is still true. So to make this generic answer more concrete, I will give you some examples coming from several different areas of mathematics. First of all, a theorem, a very classical and celebrated theorem by Zariski and Nagata, says that in our setting, so when a ideal is radical and you're over a perfect field, the M symbolic power consists precisely of all the hypersurfaces passing through each point of the variety associated to I at least M times. So if I is a defining ideal of some points, let's say in the projective plane, the fourth symbolic power of the ideal consists precisely of the curves in P2, which pass through this set of points at least 4 times. So through each of the points, it will pass 4 times. Okay? So it's a very strong geometric meaning. Now, let me give you some more reason why we care about symbolic powers. From the perspective of algebra, Nagata, in a landmark paper in 57, and he gave a talk at the ICM in 58 about it, he used symbolic powers to produce the first known counterexamples to produce the first counterexample to Hilbert 14 problem. So that is really one of the very first times where they were used in an unusual way, in a very, very unusual way. And in terms of optimization and analytic number theory also, and in some problems coming from applied math, what we care about, people care about, is lower bounds on alpha of the symbolic powers. And what is alpha? Alpha is defined to be the minimum degree of an equation in the symbolic power. So the smallest degree of the generator. Okay. Why are these relevant? Because there are certain problems where you need to, for instance, find equations of relatively small degree passing through a given set of points enough times. And well, computer can perform these computations, but you don't want to make it run, let's say, looking for equations of degree 25, if you already know there will be no equations of degree 25 passing through your points as many times as you want. Okay, so this is, generically speaking, why one wants, at least in applied math and this type of bounds in analytic number theory, they have to do with Schwarz exponents of certain kind of functions, and then there is optimization, linear algebra kind of problems, which are they have similar needs. So finding these lower bounds have again a rich history. Nagata again raised a conjecture in the same paper. It's a very celebrated conjecture, suggesting that if X is a set of at least 10 general points, and general essentially means random. One can think of it as being random, okay? General points in P2, then the smallest degree of an equation passing through these points at least m times, that's my alpha Ex symbolic m, has to be bigger than or equal than m times square root number of points. Okay. So unfortunately, this is not a theorem. This is just a proposed lower bound. And it is only known, amazingly, it is only known when R is a perfect square. So 16, 25, 36, 49 points, and so on. And it was proved by Nagata himself. He gave the proof for 16 points, but the same proof carries over to every perfect square. And there are no other results for this conjecture, despite the fact that there has been a large body of literature dedicated to this conjecture, workshops, and so on. Still we don't know much. There are weaker bounds one can ask for, and I'm just briefly mentioning Chernovsky's conjecture. Chernovsky is an analytic number theorist, just to confirm what I said, that these problems are of interest not just to algebra. And he suggests the following question. If X is any number of points in Pn, then there should be a lower bound, which is much weaker than Nagata's one, in terms of the smallest degree of an equation passing through the points, multiplicity 1, and the dimension of the ambient space. Okay. And this is known in a few more situations. Actually, this is known for very general points. And that was proved by Luisa Foley, myself, and Yishi in 18. And that was the first big breakthrough. There were a number of partial results before then, and this was the big breakthrough. And then Bizui, Grifo, Ha, and Guyen, in a series of 2 papers, they improved it. They kind of improved it, and they almost did it for general points. So I wouldn't say it's completely done, but it's almost done for general points. Still, the conjecture is that this should be true for every set of points. And I should add that Chernovsky himself did it for points in P2, no restriction. So it is known to work for points in P2, general points in P3, and essentially general points in Pn, but it's still not sure if it is always true. And Bob Lazarsfeld, a very big algebraic geometer, at a conference where I was talking about these problems, he suggested that actually he's skeptical about the fact that the conjecture should hold for every single set of points in Pn. So who knows? Maybe it doesn't work in general, but then it would be interesting to figure out what would give a counterexample if that's the case. And then we have problems coming from number theory. Yep, number theory. Eisenbach and Mazur in 97. There is the following conjecture. And the conjecture is that if P is a prime ideal in our polynomial ring over the complex numbers, then the second symbolic squared should be contained in P times the ideal of all the variables. Now, the fact that this conjecture is wide open, it is essentially only known if one can put some kind of grading on the prime ideal. If you take and a prime ideal, and there is no grading you can put on the generators to make it some kind of graded ideal, then it's still wide open. There are a few cases, almost complete intersections, and some few cases that come from linkage, but that's about it.
Oh, excuse me. I mean, the second symbolic power of P. On the left-hand side, everything.
Thank you.
Yeah.
Sure. Thank you. Yep. Second symbolics. Thanks. And the reason why they were interested in this problem is that they proved that the mistake in the first proof of Fermat's last theorem by Sir Andrew Wiles, its equivalent is an if-and-if to this inclusion over a regular ring of mixed characteristic. So in some sense, this conjecture suggests that Andrew Wiles made that mistake, but he was not that far off, because over the complex numbers, it is true, it's just in characteristic P, and therefore a mixed characteristic, that this containment fails, may fail. Okay, so there are connections with Fermat last year, the proof of Fermat's last year. Okay, and then, of course, considering the Zariski-Nagata theorem that I mentioned earlier, one would expect to have some interesting problem from algebraic geometry to be connected to symbolic powers. And of course, it is true. Essentially, everything about interpolation problems has to do with symbolic powers. So there is a wide area of algebraic geometry that is studying interpolation problems. These are very classical problems. And essentially, one can translate it in this way. If X is a set of points in, let's say, projective space, then how many linearly independent equations, hypersurfaces of degree D pass through our points at least m times? These are interpolation problems, okay, in a basic form. And these are very well studied, very classical problems in algebraic geometry. They translate easily into algebra in commutative algebra by saying that this is equivalent to study the Hilbert function of the symbolic powers of these ideals. So, especially in the case of, let's say, general points, I'm going to add this assumption now. So if you take essentially random points, there is some kind of expected answer. There is an expected number coming from linear algebra. There is a nice connector within linear algebra, and it gives an expected number of linearly independent equations. Well, it turns out that we can figure out what is this number of linear independent equations in two cases. Case m equal to 1, this is classical. I don't even know exactly who proved it first. It has been known for, I believe, at least 100 years or so, so very classical. The case m equal to 2, however, proved to be much, much more challenging, and is a celebrated theorem by Alexander and Hershowitz from the 90s. Took them 5 papers, so it's hard to write the precise date. It took them 5 papers to finish the proof. It's a celebrated theorem. And in case you're interested about this one, I wrote a paper together with Taiha. It's really a survey on this problem, on this theorem. In case one is interested, this is a survey which we wrote having in mind young commutative algebras. So we try to include everything, and it's the first paper having a self-contained proof of this result. And it's not 100 pages long. It's only 40. Only. But still, everything is in there essentially. And then there is combinatorial optimization. That is something that was completely unexpected. And the connection was drawn by a group of 3-4 authors, particularly Villarreal, work, I think, very hard to translate this problem that I'm about to write, which is one of the most famous conjecture, if not the most famous in combinatorial optimization. This is known as the Conforti-Cornu-Hayes conjecture. And this is from 1990, the year of the World Cup in Italy. So if I is a square-free monomial ideal, so it's a monomial ideal generated by square-free monomials, then remember I mentioned that usually the ordinary and the symbolic powers are not equal. There is only one inclusion. This theorem, this conjecture is not a theorem, should give a classification of precisely when equality holds. So I to the symbolic m equals I to the m for every m, if and only if I has the so-called packing property. Which I'm not going to write what it is, but it is a nice and somewhat natural combinatorial property. It's not the way that Conforti-Cornu-Hayes wrote the conjecture. They wrote it in the context of combinatorial optimization, but it was translated. So this is completely equivalent to the original conjecture. And in case you, and just a bit of curiosity, I think in 2001, one of the two authors wrote essentially a monography, which included a small set of conjectures, open problems in combinatorial optimization, which he felt were really important for the area. And he assigned a price of $5,000 American dollars to those who would solve any of these conjectures. And the Conforti-Cornu-Hayes conjecture is one of them. Unfortunately, this paper, this monograph, was written in 2001. And it was written that the prices are only valid if the solution is discovered in the next 20 years. So even if we solve this problem today, we will not get the $5,000 prize. Still, well, it was an interesting curiosity. And this is called the max flow mean cut conjecture in combinatorial optimization. Max flow mean cut. And then, of course, I should include something from commutative algebra and some algebraic geometry, as Brian Harbour would say. And these are a class of problems which is very challenging. It's called containment problems. They ask for which m and t do we have that I to the symbolic m is contained in I to the t. Okay. And there are a number of interesting results by a number of strong authors. For instance, Ein, Lazarsfeld, and Smith proved the first general bound in 2000 over the complex numbers. Oxter and Juneke in 2001 generalized it. Both papers are on invenciones. And then Ma and Schweid proved the mixed characteristic case, I think in 19. So this is to find for any ideal I, there are some m and t's for which you can naturally find this inclusion. And the inclusion they find is a non-trivial inclusion. I'm being a little vague here, but it's not super related to the rest of the talk. So, and then there's a number of other results by Arbon, Eloisa, and many other authors that I cannot write. Okay. And why there is some algebraic geometry involved? Because I talked with Brian Arbor several times about these problems, and I asked him what is, I can see an algebraic interest, but what is the geometric interest in this type of questions? And he gave me an example. For instance, if you take some points, I think in P2, yes, I think it's in P2. If you take a set of points in P2 and I is the corresponding ideal, then it is this Ein, Lazarsfeld, and Smith, or Oxter, Juneke, and Schweid essentially proves that the fourth symbolic power of I is contained in I squared. And Craig Juneke pushed a conjecture that has been there for a bit, suggesting that actually I symbolic cube should be contained in I squared. And Craig proved it for general points, so for random points. However, it turns out that there are counterexamples in general. And all of these counterexamples seem to have very interesting geometric features. So there is some algebraic geometry in the sense that there is some kind of expected containment, some expected inclusions. And when you don't have them, is because something interesting happened at some algebraic or algebraic geometry level. So that's the connection. So I mentioned a number of areas, and I quickly give you an idea of a short list of open problems. On each of them, I could easily talk for, I could give 2 or 3 talks at least on each of these questions. For some of them, probably would require 5 or 6 to cover the literature and explain nicely what is really going on. So this is to say that there is much, much more than going over in this talk. This is more like a talk which may make some of you interested into this type of questions. Okay. So considering that there are all these problems related to symbolic powers, there is a couple of natural reasons one may wonder why all these problems are still open. One possibility is that the area is young. When an area is young, there is a lot of open problems because not enough people work on it, or they were not good enough, so to say. And this doesn't seem to be the case for symbolic powers. We've seen problems coming from 1957 from Nagata, who is an ICM speaker, and he won many prizes. We've seen Oxter, Juneke, Ein, Lazarsfeld, and Big Shots, Arborn working on these problems. So it's not the lack of problem. It's not the lack of people working on the problems. It's just that it must be the other option. If it is not because the area is young, then what is it? The problems are hard. But why the problems are hard? What is that in particular, if you need to point at one element that makes it super hard, is we know how to write the generators of I to the m, the ordinary powers. We just don't know how to compute the generators of I symbolic m. It's just hard. We know, in theory, we know the primary decomposition, but that's not enough to tell us something about invariance of the ideal, like Castelnuovo-Mumford regularity or degrees of minimal generators, or Betti numbers, or Hilbert function, or anything else. So this is the hard part. Okay? So in this project with Cleto and Uwe, we try to work a little bit to provide an additional tool to try to help. Maybe not necessarily for all these open questions, but still to understand better symbolic powers. So we're going to work on a formula. So in general, what we've seen in the very first example carries over for any ideal I. What is it? The fact that if you take the usual power I to the m, this is equal to the symbolic power intersection, and then there are some extra components. Okay, so if you look at the associated primes of the m ordinary power, you get the same components as the symbolic ones, and then you get extra ones coming from these additional ideas that you need to intersect. Okay. And I want to point out that this gamma m is crucial, because gamma m is the empty set if and only if I to the m equal to the symbolic m. So we have extra components if and only if the two ideals are not equal. Okay. So the natural ideal that has been tried by and used by other authors, many other authors in the literature, is I know how any computer or any person can essentially compute I to the m, the usual power. I just need to take the product of any m generators. So I know how to compute this ideal. So what I need to do to get the symbolic power out of it is strip away, remove, essentially, these extra components coming from gamma m. Okay? So these are the ones that we need to get rid of. And there is a theoretical formula that was used by many authors, notably Herzog, Eby, and Chung, but many other authors after, and I believe even before them. So if you call S star of I to be the union of all these extra components that you get for each symbolic power, then you can define an ideal K, which is the intersection of all these primes. And you can obtain the M symbolic power. That's the formula that I'm reading now. The M symbolic power of I is just obtained from I to the M by coloning out some large power of this ideal. So the colon condition, which is very simple, I believe it's even defined maybe in chapter 1 or 2 of Atiyah McDonald, it's actually removing components. That's what it does. So when you colon out by K to the T, you remove these components, okay, these extra components. And that's why the formula works. The problem with the formula, however, is that this is theoretical. This is not practical. It's useful to prove abstract results, but it's not very practical because we don't know, in general, what is the ideal S star of I. There are very nasty examples, even when I is a square-free monomial ideal. And there are very nasty examples of ideals that have some associated primes, which are stable for a while, and then after being the same for 3,000 powers, then some new prime suddenly comes in. So in general, knowing exactly what is S star of I is hard. It's very hard. In general, even for square-free monomial ideals. Just make it clear. So our suggestion here is to replace K by something which is more computable, something which is more concrete, so to say. Again, it's not like it's going to be better than S star, the ideal K that they used earlier. It's just that we have a different goal in mind. And with the goal we have, we get something new. The only problem now is that when you want to replace K by something else, you need to know what that something else should be. And we were not the first one to try to find something else. So our first theorem will tell you what is that something else. And I want again to point out, just to illustrate Clayton's relevance in this project, that he was actually the one who figured out what the alternative to K should be. And then we end up, and then eventually we did prove his idea of what that should be. So he had a very good intuition there that lead us to, and again, it's not the most natural ideal one would think of. So it was, in some sense, it was very nice suggestion for him. So to tell you what is the concrete ideal, I need to remind you what is the presentation of an ideal I. So the presentation is the first steps of a resolution. So when you look at the CZG matrix of I, the C fitting ideal is generated by the mu minus C minors. So the subdeterminants of this matrix phi, you have some natural matrix phi, and you look at the subdeterminants of a certain size, mu minus C. I call it mu because usually mu is the number of generators of I. Okay? And I want to make it super concrete. Let's go back to the first example, xy, xz, yz. The codimension, the height is 2. So when you look at the CZG matrix, if you get this CZG matrix phi, how do you get it? Well, the first column says if you take the first generator and multiply by z minus the second generator times y plus 0. Well, if you do the math, that's xyz minus xyz, which is indeed 0. Okay, so it's not super hard to get this CZG matrix. And then the second fitting ideal is just the ideal generated by the entries of this matrix. So it's xyz. It is something that is computable. Okay. And the theorem that we did prove, I guess first I need to tell you a fact, an interesting fact about fitting ideals is that the primes containing the fitting ideals are precisely the primes such that I localized at P is not a complete intersection. So the minimum number of generators of the localization is strictly larger than the height of the ideal. So our first theorem, our first main result, is that there exists a T large enough such that I to the symbolic M, it's I to the M colon FCI to the T. So we do find one of these formulas similar to the one above, except that this time it's a very nice ideal that any computer algebra software or anyone can essentially compute. And I give you quickly the idea of the proof.
Paul, excuse me, let me just remind you that this works for generically complete intersection and mixed radius. I must be a mixed.
Yes, it's one of the running assumptions is that I is a mixed radical.
Radical, right, great, yeah.
For simplicity. And I wrote earlier that actually that's the highest generality.
Oh, I see, great, yeah. Thanks.
And R can become a column. I just wanted, especially for the definition of symbolic powers and so on, I wanted Zariski Nagata, I wanted I to be radical, just for that. Okay. So the idea of the proof here is essentially we need to show that if Q is one of these extra components that we don't want in I to the M, then Q contains this fitting ideal, i.e., I sub Q is not a complete intersection. So the bottom line, at least in our setting, is that we just need to show I sub localized at Q is not a complete intersection for any of these additional associated primes that the ordinary power has compared to the symbolic power. And this is true because since Q is gamma M, then Q is an associated prime of R mod I to the M, which means it is also true after we localize at the same ideal Q. So this means that I sub, oops, this is moving, then I Q raised to the M has an embedded component. Which is Q. And by the fact in section 1, dimension in section 1, this automatically implies that IQ is not a complete intersection. Because this implies that the ordinary and the symbolic powers are different. Okay. So roughly speaking, that's the core of the idea. As you can see, it's not super complicated to explain it. The hard part is coming up with the guess. And as I pointed out, that's where actually, I'm glad that Clayton came up with these guys. A corollary here, which is nice, is that if you remember the Conforti Korno-Hayes conjecture, the one with the $5,000 prize, was asking about when is it true that I to the symbolic M equals I to the M. Well, that happens for some M, if and only if this ideal, the fitting ideal, contains an element which is R mod IM regular. So it's a non-zero divisor of R mod IM. Okay. And this gives a nice way of characterizing when the symbolic powers equals to the ordinary powers. And in general, for the Conforti Korno-Hayes conjecture, or the analog for non-square free monomial ideals, it helps because then you can ask Macaulay or any computer algebra software to tell you if I to the symbolic M equals I to the M for relatively small powers. Okay? For large powers, it's going to be computationally expensive. If you just ask it to compute both of them and check if they're equal, it will take forever. This takes a little less time. Okay. And here is a quick example. if I is the ideal generated by the 3 by 3 minors of this matrix. Well, in this case, we have a presentation with CSG matrix can be written explicitly. It's not super hard. It is negative y z w x minus y z minus t x minus y. It's kind of a nice structure, right? And there we go. That's what the matrix is. So now this ideal has height 2. Okay. So F2 of I in this case, since this ideal is generated by 4 matrices, this is going to be I2 of phi. So we're looking at the 2 by 2 minors of this matrix. So in particular, we can look at this one. This is xy minus zt. And one can check xy minus zt is R mod I m regular for every m at least smaller than or equal to 7. Why 7? Just because afterwards the computations become very expensive. And indeed, there is actually one can use some other theorems in the literature to prove that it is always R mod I m regular for every m, which implies I to the symbolic m equals I to the m for every m for this ideal. But you see, this corollary gives us some computational advantage in having the right guess. This is an ideal for which it should be true. And let's work and prove that in fact, for these ideals, the symbolic and ordinary powers are equal. Okay. Then the other part that we are left after we discuss all this area is finding effective exponents in the formula. Remember, we have I to the symbolic m equals I to the m column some power, some large power possibly of this ideal. Okay. So we want to find effective exponent. And there is a conjecture. This relates nicely to a conjecture by Eisenbach and Maser. Who ask the following: if I is generated by the 2 by 2 minors of a 2 by 3 matrix of general linear forms in a polynomial ring with 3 variables. That's what they're saying. Then I to the m equals I to the m colon f2 of I in this case, because the height is 2 equal. This is not exactly the way they phrase the conjecture, but it's completely equivalent. It's very actually easy to check that they are equivalent, the two conjectures. Okay. So this shows that there is general interest. It's not just us wanting to find the exponents. This has to do with understanding the annihilator. It has to do with understanding the annihilator of the module I symbolic m mod I to the m. And our theorem here is that the conjecture is true. And actually, we prove it in higher generality. Again, remember, I is a radical ideal. Let's say that it has Castelnuovo for regularity equal to 2, number of equation, which is c plus 1 choose 2, where c is the dimension of r minus 1. Then I to the symbolic m equals I to the m column fci, and then we need some slightly different formula, which depends on the height. In the previous case, c is 2. So if you plug in c equal to 2 in the second equation, the one we proved, you actually recover Eisenbach-Maser conjecture. Okay. And moreover, we prove even something stronger, and no smaller power works. So this is the best one can do. Okay. So the problem, though, is that this result, for which we actually were pretty happy to prove, is that it only works for very narrow class of ideals. Yes, it does prove this conjecture by Azebad and Mazur, but we were really looking for a T which would work for every I, not just for very spatial, for a class of ideals I. So we started working on it, and that's actually this next result was the one that took probably the longest for us to figure it out, but eventually we did. And it says that in general, so no restriction on I, in the most general assumptions that we have, I to the symbolic m, oops, okay, let's try again. I to the symbolic m equals I to the m, colon, what power do we need? Well, we need m minus 1. Okay. So, for instance, if you want to compute the symbolic square, you just need to column with the ideal, the fitting ideal. And if you want to compute the symbolic cube, you just column with the square. So for a general m, this exponent that we found, which is very good already, sometimes it is sharp, it is the best you can do, and sometimes it is not. But that's expected when you have such a general one that works for every I. I would expect that if you restrict to smaller classes of I, one could maybe make it even much smaller. Like for certain class of I's, I would expect even m over c to work, for instance. Okay, so like in the previous formula, in some sense. Anyway, I want to give you a quick idea of the proof. There are 3 steps. Step 1, which employs an idea of Craig-Uneke, essentially, is that if delta is one of the minimal generators of FCI, then there exists a complete intersection inside I, such that 2 things happen. Delta is in the colon ideal C colon I. And additionally, this colon ideal R mod L has nothing in common in terms of associated prime with I. So they have no common components. This is what people called, and that was the way, that's how he found it out. This is called the geometric link in linkage, which is a very well established, it's a nice theory that was mostly developed by, from the algebraic side, from Uneke and Ulrich. So he essentially allows with this step to let linkage into the picture. And then step 2, the one that is doing most of the heavy lifting after we have now Craig's idea, is that to prove that if you take the ideal L that we just defined and you multiply by the m symbolic power, then you are inside the m minus 1 symbolic powers times I. Okay, that is the one doing the most heavy lifting. Step 3, which explains why we care about step 1 and 2, is to observe that it's enough to show that FCI m minus 1 times I symbolic m is contained in I to the m. Okay. This is a small lemma that one can do. And it helps because usually proving that an ideal equals a colon requires a double inclusion, but essentially step 3 says you just need one inclusion, which is actually the easy one. In general, it is easier to prove that the product of 2 things is contained in another ideal compared to many other problems one can have. And then step 4 is to just take m minus 1 generators of the fitting ideal. So we need to prove that the product of them times I symbolic m is contained in I to the m. But when I do that, I get this. And by step 3, I know this is contained in I symbolic m minus 1 times I by step 2. Sorry. So this is contained delta 1 delta m minus 2 times I m minus 2 minus 1 times I. And then you just keep going. By step 2, this is containing the I symbolic m minus 2 times I, and so on. Until at the end, you get everything that you wanted. Well, technically, you get this, which is I to the, sorry, I to the m minus 1. Okay. So we need some technical results. We need some work, of course, as expected. But at the end, we obtain the formula that you wanted. And one reason why one would like to have this type of effective bound is that now you can get as a corollary that the initial degree of a symbolic power in our setting can be bounded below in some way. Okay. It's not maybe the prettiest of the formulas, but it is a formula. So we do get a lower bound. If you remember, this was one of the problems in our list, finding lower bounds. The one we found sometimes is sharp, not very often. Sometimes it is not, but at least it explains why one cares about having this, why one cares about having this effective bound in the formula. Now, Cleto, to explain the conjecture, I probably need 3-4 minutes. I would be very fast, but I don't know if I have those time, if I have this time.
Yeah, you have it. Yeah, go ahead.
Okay.
Great.
Thank you. Then I will very quickly, briefly mention a conjecture. I already mentioned quite a number of open questions earlier. I just want to give you one more that, again, was stimulated quite a bit by Cleto. He ran many computations, and he was really the one suggesting this conjecture. So that's another place in the paper where his contributions were really, really fundamental. So for every G in R, we can define the Jacobian or gradient ideal to be the ideal generated by the partial derivatives. Remember, we are looking at the polynomial in a polynomial ring, so we can always take partial derivatives. That's an R ideal, okay? And we can define the symbolic defect of IM as the minimal number of generators of I symbolic M, which are not in I to M. Let me give you an example. Remember our favorite example, XY, XZ, YZ? So if you look at this case, then the symbolic defect, the second symbolic defect of I is 1, because I symbolic square is I squared, and then I need one extra element, XYZ. This is the one. I need one more element in order to get the symbolic square. Okay. And I'm going to call this element G. Okay. So now for this G, the Jacobian or gradient ideal is, of course, the ideal YZ, XZ, XY, when you take partial derivatives. Okay. Wait a second. We know what this ideal is. This is just I. So it feels almost like magic. Like you add an element to I squared to get I symbolic square. You take the partial derivatives, bam, back to I. That's interesting. And I believe these and similar examples, Cleto ran a lot of examples, motivate this conjecture that really I should credit to him more than anyone else. If the symbolic defect of an ideal is T, this means we need T equations to add to I to the M to get I symbolic M. Then there exist elements that we can add there, such that, so we can add these GIs in order to get the symbolic power. And so this is the first condition. And on top of it, for technical reasons, we may need to take radical, not just the Jacobian ideal itself. So if you take the sum of these ideals and you take the radicals, you get back I. Remember, in our setting, I is already radical. In the general case, they will be equal to radical I. Okay. So, so that's the conjecture, that this behavior, it doesn't happen by chance. It should happen way more frequently. And I will finish with two remarks. We don't have essentially any case where we know it is true. We only have a lot of computational evidence. So this implication, this inclusion, holds always by Zariski-Nagata. Essentially, it's a consequence of the Zariski-Nagata theory. So the other inclusion is the interesting one. And that's the hard one. And secondly, for some I, one has to take the GIs to be non-homogeneous. So even if your ideal is homogeneous, in our case, once you look at these elements to add to I symbolic, to I to the m to get I symbolic m, you may need to go for something which is non-homogeneous if you want this to be satisfied. Here is an example. 1 second, there we go. If I take xz, zw, yw, yt, and zt, this is an ideal of multiplicity 5, second symbolic power equal to the second ordinary power, but the third power is different. You need to add the product, the monomial generated by the product of all the variables. Okay. This is generated in degree 6. And of course, this ideal has, this element has degree 5. But in this case, the Jacobian of G is radical already, and it is much smaller than I itself. Multiplicity is 10, while this ideal is multiplicity 5. So this means I cannot use this G itself. So instead we need to take G plus a polynomial of degree 6. And that's why it's not homogeneous. This one has degree 5, if you remember. I need to mix degree 5 and degree 6. So in order to solve this problem, one needs to be willing to sometimes to have to use non-homogeneous equations. Well, thank you for your attention.